I'll start recording. Okay, we were talking about the chemical reaction last week, the different kinds of chemical reactions. Once again, I'm going to leave my screen on. That way, if it boots me out, I will see, because it's hard to see that when I don't have this chat screen here. We're talking about the different types of chemical reactions and how to identify them based on the template or the format of the equation. So we're picking up where we left off. Now, while we're here, I want to talk about how to complete the reaction. At some point, we will get towards that when the chapter is over, but I feel like completing the reaction goes hand in hand with recognizing the types of reactions. So I want to talk about it right now. So this is completing the reaction. Let's see. So in the 5 reaction types that we talked about, there are a few that are predictable, where they follow a certain pattern in the reaction where you can easily determine what the product should be. And then the few that are more complex. So let me start with the predictable ones. That will be the synthesis reaction. So going all the way to the beginning. For the most part, synthesis or combination, you're combining to make one compound. So, and then not only that, most of the time the compound is ionic. So let me start with this real quick. As we're trying to identify the reaction with synthesis, so I'll say synthesis, single replacement, and double replacement. When it comes to these reactions, so yeah, synthesis, single replacement, double replacement. For these reactions, I'll say use ions to determine product. Okay. So for these 3 types of reaction, the synthesis, when you're combining them, single replacement, double replacement, you want to use ions. And here, right here is the key. You want to ionize them. So use ions or ionize. Ionize. For the other 2, we do not ionize. Okay? So make sure you're ionizing these. I'll just say ionize. That works. Okay? What do I mean by that? Let's do a quick recap. With the synthesis reaction, you are taking elements and combining them to form a compound. So what they're saying here is, as you're bringing them together, you want to ionize them. Don't just squish them together. So don't just take element 1 and element 2 and then write them side by side to make a compound. What you want to do with these 2 is ionize the elements, ionize them, ionize, right? And then when you form the ion, most of the time, the one that's metal will form a positive ion. So depending on which is which, let's say that the first element is a metal. If it's a metal, it will form the positive ion. If it's a non-metal, it will form the negative ion, right? And once you have that, you will crisscross. So crisscross to make product. Okay? And so as I walk through the following steps, the steps I'm about to show you, this is what I'm going to be doing. I'm going to remember, since this is reaction to get the product, I have to ionize. Okay? So I'll give an example of this and I'll show you how I ionize. Let me erase all of this. Now do this step by step to show how I ionize. For example, let's say we got sodium, solid, plus chlorine, gas. Remember, chlorine is part of that Brinkerhoff family. Brinkerhoff. So this is the Brinkerhoff where everything is sub 2 exists as diatomic in real life by themselves. So chlorine by itself will be Cl2. It is still considered an element because the atoms are from the same element. Okay. I'm going to ionize these to form my compound. So until I get them together, I can't say the compound will be NaCl2. This is not correct. Okay, I can't just write the formulas side by side and say this is a compound. This is not correct, okay? So what I'm going to do here is I am going to ionize this. So as I ionize, okay, I guess I should write this in the middle so I don't have to write this twice. I'm ionizing both of them. As I'm ionizing these, sodium metal becomes sodium ion. Chlorine gas becomes chloride ion, right? Based on the common ions we learned. Now I can crisscross. So I'll crisscross. And I know that since each of these has the same but opposite charges, I can just say N. The negative one will come here, Cl. The positive one will come here. But in the compound, these subscripts drop off. So in the compound, we get NaCl. So now I write this compound right here, NaCl. Remember, to form the compound, you took the positive one from the sodium, crisscrossed it with negative one from the chloride. The negative one came to the bottom of the sodium, positive one bottom of the chloride. They drop off because they're equal but opposite. They kind of neutralize each other. What we're saying here as we combine these two is it takes one sodium that's positive, one chlorine that's negative to make a neutral compound. We want to combine the number of positive ions and negative ions until we get a neutral compound, right? So all it takes is one of each. Okay, now that we've done all that, then we're going to try to balance. That's a whole different process in and of itself. To balance the equation, then we say, okay, let me see how many sodium ions I have, or sodium atoms. How many chlorines do I have? In the compound, same thing, right? So when by examination, I look and I see the sodiums match, so they're quote unquote balanced. Chlorines don't. I double the ones to the right on the product side. I have to double sodium because they're in the same compounds. So it's going to be 2 here, and then that forces me to make the sodium on the left 2. So this is going to be 2. This will be 2. Remember, I'm writing the coefficient in front of the formula. So this is now balanced. That's what I'm saying. I feel like completing the reaction goes hand in hand with balancing the equation, right? When you have synthesis, don't just squish the elements together. You want to make sure that you actually ionize, crisscross to get the product. Okay. Let me move on to the next one that has the same or similar format, similar process. That will be your single displacement. Okay. So, second type of reaction that undergoes the same kind of transformation is single displacement. In single displacement, what we see here is the formula I showed you guys before was the element is added to a compound to give us an element and a compound. So for this, let me pick another element. Let me see. Think. I think I'm going to do something with sodium again. So sodium by itself plus the compound here will be HCl again, right? And then I'm trying to figure out what my product will be, right? Like before, you want to ionize and then crisscross. So ionize and then crisscross to get your product, okay? So let me go ahead and ionize the reactants first. I will ionize. When I ionize this, for sodium metal, I get sodium ion, Na+. For HCl, for the first element in the compound, I get H+. The second one, Cl, Cl-. You see that? This is the context of a compound, right? Now, we have to crisscross, but we cannot crisscross the same elements that were in a compound that will redo what we had. We have to switch. So even though I said crisscross, we really have to switch first before we crisscross. So switch partners. Okay, so when I switch here, sodium ends up with chloride, and then hydrogen ends up by itself. So on the product side, I guess I can write it side by side right here, that sodium ends up with chloride and then hydrogen by itself. But wait a minute before we conclude this. Isn't hydrogen part of that Brinkelhoff family? Yes, it is. So when it's by itself, it ends up as H2. So it combines with the opposite version of itself and ends up as H2. So to make the compound here, I am going to crisscross these, okay? I'll do it on the left and then I'll do it on the right again. Crisscross the charges again, crisscross this here, end up with Na minus 1, Cl plus 1. These drop off, and you end up with NaCl. So that's what I'm going to be doing up here. These combine to form NaCl. I know I've kind of switched them around, but you get it. The product is NaCl, and then H becomes H2. So because this is Brinkelhoff, the hydrogen is part of the Brinkelhoff family. It combines with a negative version of the ion formed, and that's how it's able to form H2. And H2 will be a gas, okay? So this helped us complete our equation. I do have a compound here. I do have an element here. So I guess I want to modify this top part here to match with my product. C, E, same thing, just different order. Okay, now I can go through and balance. In order to balance this, let me remove this up here so I can have some space. To balance like before, I'm going to go through and itemize. I have one sodium on the left, one hydrogen on the left, one chlorine on the left. On my right, I have one sodium, one chlorine or chloride, and then two hydrogens. So when I look at my number of atoms or elements by examination, everything matches but the hydrogen, right? So to make the hydrogen on the right match the one on the left, I have to multiply the one on the left by 2. So times 2. But since H and Cl are in the same compound, I have to multiply by 2 twice. 2, 2, right? But in doing so, even though I've now balanced the hydrogen, I've messed up the chlorine. Now I have to go to the right and double the chlorine. But chlorine and sodium are in the same compound, so I have to double that too. So I end up with 2 here, I end up with 2 here. Let's see. Now the sodium has to be doubled on the left. You see that? So it looks like as far as balancing is concerned, everything is 2. But the coefficients here, the multipliers become the coefficients. So I have to make sure I go through. This becomes 2 here. This is 2 already written, and this is 2. So 2, 2, 2, 1. Yeah, it's now balanced. Okay, so in single displacement, once again, we ionize to crisscross. I'm going to stick with the theme of sodium chloride, or at least compounds like that. Okay, so sodium, hydrochloric acid, sodium, chlorine, gas. And now I'm going to look at sodium again in the context of a compound. So in double displacement, we're doing the same thing. We're ionizing and crisscrossing. But double displacement, this time we have compounds all over, right? So compound plus compound to give you compound plus compound. But again, you ionize and then crisscross after you switch. Okay? So I'm going to start with sodium hydroxide and HCl. So I figured I stick with similar element type so you can see how it translates from an element to a compound, from a compound and to two compounds, right? From both elements, one is a compound and then both are compounds. Okay, once again, ionize here. I will ionize first, and you can see that. Sodium ion, hydroxide ion, hydrogen ion, chloride ion. Now I've already ionized these. I'm going to crisscross these to form products. Sodium will go with chlorine, and I'll write this here as sodium and then chlorine. Hydrogen will go with OH. Hydrogen and then OH. Okay? So Now, these, because they have the same but opposite charges, will just combine to form sodium chloride. And then here, these two, sorry, it's OH minus. This will form H2O. Okay? So I just switch them, and then I combine them. And then now I have my product. Now, to balance this, the third way is normally how I write it. Let's see. How many sodiums do I have here? 1. How many OHs? 1. How many hydrogens? 1. How many Cls? 1. How many sodiums? 1. How many Cls? 1. How many hydrogens? 2. How many oxygens? 1. Okay, let's see. Number of sodium equal number of chlorines equal, right? 1 and 1, 1 and 1. Okay, now we're trying to figure out how many total hydrogens do we have on the left. If you combine the hydrogen from here, right? I should have, you know what? Instead of combining the hydroxide, I should have left it as O and H. That would have worked better. O is 1, H is 1. How about that? Much better? Yeah, because there's no hydroxide on the right, the way it's written here on the left, so I'll leave it like that. So number of oxygen, 1 and 1 balances. Number of hydrogen, if you add these two hydrogens here, it equals 2 hydrogens. On the right, we have 2, so this is balanced. So this equation is balanced, okay? Same number left and right. Okay. So now that I've seen all this, completing the equation, balancing the equation, with this combustion reaction, as you can see right here, you usually have your fuel, you have your oxygen, and then, so I want to write this before I continue with the rest of this chapter. Because you see that over and over again, and you can pay attention to that. So with combustion reaction, you have a fuel, and the fuel has the following arrangement, right? Format. CXHY. Sometimes it's CXHY or CXHY and then OZ. It doesn't, it is either in this form or in this form or something similar. A nonmetal and a hydrogen, or a nonmetal, a hydrogen, and an oxygen. And this is then being added to oxygen. So I write here CXHY plus oxygen. So in a combustion reaction, you have a fuel right here. You have oxygen, because this is necessary to burn anything. On the product side, you have 2 oxides. One will be the oxide of the first element, which is carbon, in this case, carbon dioxide. The other will be the oxide of the second element in the fuel, which will be water. Okay, so in a combustion reaction, at least the one where you have carbon, hydrogen, and oxygen, or carbon and hydrogen only, you tend to get carbon dioxide and water as your only product. Okay, and so water is a must. And then here you have an oxide. Now I have seen some do this, like sulfur, hydrogen, say like SH4 plus oxygen. In that case, SO2 plus H2O. You can see the sulfur getting 2 oxygens to form that, and then the hydrogen getting 1 oxygen to form this. Okay, but the one that you definitely want to remember is this one here. This is the most common one, and this is combustion reaction. And in combustion reaction, you have a compound, an element, a compound, and compound, right? And then finally, we have decomposition reaction. With that one, I'll tell you right now, it's difficult. You can't just ionize to get products. So decomposition reaction, usually you have to just memorize it. Okay, so I'll say here, decomposition reaction, you memorize. Has to be memorized. So what I would do before an exam, because we didn't have note cards or any, it wasn't an online class, I would just memorize it right before the exam. We're memorizing it like all weekend long, all the time before the exam day. And right before the exam, I would just like try to memorize it real quick, get my exam. I don't even write my name. I write stuff that I feel like I'll forget real quick and then move on from there. Okay. Okay, we're now moving on to stoichiometry. With stoichiometry, we're dealing with the quantities of the reactants and the products and how they relate to each other. Okay? The coefficients in the chemical reaction specify the relative amounts in moles of each substance involved in the reaction, meaning that once you have your balance equation, now what? What are we trying to get from the balance equation? We're being told from the balance equation, once you get that, okay, C8H18 plus 25O2 16 CO2. So imagine we just balance this equation, right? Now what? Well, the information, the balanced equation provides us with the relative amounts of each reactant required. So here we have the relative amounts. So in chemistry, we tend to focus on relatives a lot. So not like your relations, like cousin, brother, sister, but one to the other, right? So we can look at relative amounts. For example, relative amounts of reactants. That means we're comparing the amounts of reactants required in the balanced equation. For the reactants, we can use the coefficient, the multiplier, to compare. If we are going to have two amounts of the fuel, which this fuel is called octane, how much oxygen do we need? So from the balanced equation, this is going to be oxygen, right? We can say for two amounts of octane, we need 25 amounts of oxygen. Okay, now I left the term amounts because amounts is more general, right? But what I'm going to do is then replace the amount with a specific number. The numbers here in the coefficient, the multipliers used to balance the equation, are usually read. The more common way to read them is in moles. So in the part, the amount, I can replace the word amount with moles. So 2 moles of octane. When we use that, we need 25 moles of oxygen. It's very important to understand what the balance equation is communicating, because it's not just, we're not balancing it just to balance it, we're balancing it also to communicate to the person reading how the amounts of the reactions are related to each other. Okay, then products. If we use that amount of reactants, how much products do we get? Well, we yield 16 moles of carbon dioxide and 18 moles of water. So from here on, I want to mention this. In stoichiometry, we tend to deal with two amounts in one time. So I'll say here, in stoichiometry, we deal with two chemicals at, at one time. Okay? So stoichiometry is the calculation we do, it's the method we do where we use a known amount of one of those two reactants to figure out the unknown amount of the other reactant. So remember how I said here, we're dealing with two chemicals at one time? One chemical has a known amount and the other chemical has an unknown amount. Okay, so we're always dealing with two chemicals at the same time, two chemicals in one time, but one is known. So we go into the problem knowing how much it is, how much is available, and we use the known to figure out the unknown. Okay, So use the known to determine the unknown. Okay? And this is a method that is seen throughout chemistry, right? You really want to know something about a secondary chemical, but then you work with a different chemical because that chemical will give you the information you need about another chemical. Okay? And so here they go into stoichiometric ratios. And so what I'm going to do here is go straight to this slide here. In this slide, I want to talk about how to figure out what is called a mass to mass ratio and a mole to mole ratio. So let me start with the mole to mole ratio because it starts with that over here. So from the balanced equation, we also get a mole to mole ratio. So what is a mole to mole ratio? The mole relationship we talked about before, where we know the mole of one chemical and the mole of the other, if we write those as a fraction, the ratio is just a fraction. Okay? When we write those as a fraction, we essentially wrote a mole to mole ratio. Okay? So going back to this balanced equation right here, I'm going to write 3 mole to mole ratios real quick from this balanced equation, because you want to practice and know how to write a mole to mole ratio. What in the? Okay, that's okay. I'll address that in a little bit. Oh, hold on. What is? Okay, sorry. Stop just started falling in my kitchen. Okay, so mole to mole ratio. With the mole to mole ratio that we have here, I'll just pick 2, okay? So 2 chemicals, that's what I need to pick. I'm going to highlight them as I pick them. This yellow one and this yellow one. That's going to be my first mole to mole ratio. So my first one will be 2 as in the coefficient here, moles, C8H18 over 25 moles O2. Okay, that's my first one. I'll color this yellow to stick with the theme. Okay, next one, let me pick a different color, different combination. How about this and this? It's going to be my green. Okay. For the greens, I'm going to go with 16 moles CO2 over 18 moles H2O. Okay. Here. Okay. Now for my third one, since I mixed up the colors, let me go with this and this. Okay. So 25 moles O2 over 18 moles H2O. Of course, I combine these 2 different colors, right? So the H2O is green, the O2 is yellow. Doesn't really matter. But the point is, I just picked 2 chemicals each time when I wrote my mole to mole ratio. Any 2, right? Since you can combine any 2 chemicals, from what you just saw me do, the question is, how do I know which ones to combine when I'm solving a problem? Do I just write all of them? No. So then which 2 do I use? It depends. In the equation, in the question, you will be given. So in a question, you will have the given amount formula and wanted. So you will use these, the given and the wanted formula. So those are the 2 you're going to actually use, okay? So tell you this is given, this is wanted, and you use those 2. Okay, so knowing all of this, let me go back here. Wasn't there something that was given to us here? Oh, here. How many how many, this is wanted, right? Because they're already asking a question. How many moles of CO2 form? Okay, hold on a second. Let me write down real quick. What is wanted according to that question is number of moles of CO2. Okay, let me go back to this. If 22 moles of C8H18 are combusted, burned, oops, back here, given 22 moles of C8H18, right? So the reaction amount is 22 moles of C8H18, and then wanted is CO2, right? So seeing that here, let me go ahead. What I like to do in the balanced equation is, let me see, let me erase this. Oh, okay. I like to write G over the given amount and then W over the wanted amount. So the given amount is 22 moles, right, of this formula. The wanted amount, we're trying to figure it out, so we have no idea what that is, which is going to be this number here. Whatever that is, the unit will also be in moles. So when we write our mole ratio, we're writing our mole ratio for these two formulas right here, okay? So in the stoichiometry, wait, let me go ahead and erase this because now I need the space down here. In the stoichiometry, when I'm working things out, we are going to start our stoichiometry, or we're going to start our dimension analysis with a given number. Ah, I hate that this is in layers. Okay, hold on. I just erased the first layer. Okay, finally. Let me copy and move this up so I can see the other question. Okay. So you start with a given number right here. So I write 22 moles C8H18. Dimension analysis, right? H18. Then you draw your dimension analysis brackets. Remember, here we'll use a conversion factor from the balanced equation. We're going to be using our mole to mole ratio, where the bottom part of the ratio has the moles of C8H18 and the top part has the moles of CO2, right? So like we had before, this is the moles of C8H18, 2. This is the moles of CO2, 16. We multiply this out and it gives us what we want because you see this and this cancels out. The units we don't want cancels out, leaving the units we want, moles of CO2. So 22 times 16 divided by 2, 176. Okay? Yeah, 22 times 16 divided by 2. That's it, 176 moles of CO2, just like that. So the mole to mole ratio was used here. Once we learned what the mole to mole relationship was, stoichiometry, we got that. Then we use that relationship that we know to then figure out how much CO2 should be made if this amount of the reactant is used. So mole to mole ratio is used in calculation. When we're using it, that's called stoichiometry. You're using one to get to the other, right? This reminds me when I was younger, you know, yeah. People kind of try to friend you, but they really want to know your friend, not you. But yeah, that one is a little bit more simpler than stoichiometry, but kind of something like that. We're using one chemical to get information on another chemical, right? And so here they have a mole to mass to mass conversion. So you can go from moles to moles, moles to mass, so many different units of so many different amounts of the chemicals in the balanced equation. So they're saying, let's say A is your reactant and B is your product. You can go from the mass of A to moles of A, stoichiometric ratio B to A. That's the moles to moles from the balanced equation, right? Moles to moles of B to A, then moles to B, and then mass of B. Moles of B, the mass of B. Once again, we're using A to really get to B, right? So let me go ahead and rewrite what they have here. If you're going from mass of A but you really want mass of B in a balanced equation, then in your conversion, you write out in your dimensional analysis, you start with mass of A, you will write out your conversion brackets. You actually end up with three conversion factors. Okay, there are three of them going from mass of one thing to the mass of the other, three conversion factors. The first one is you get this from the periodic table. Second one from the balanced equation, that's your moles to moles ratio. Third one from the periodic table. So what I do when I'm teaching this and people are first learning this, I use the acronym PTBEPT, just saying that you need to use three conversion factors to allow you to transition from mass of the one chemical to the mass of the second chemical. Okay, from the periodic table, you will have here 1 mole of the chemical A, and then here you have the mass in grams of A. That's the periodic table mass. So the mass is in the periodic table. BE, this is the mole to mole ratio from the balanced equation. You have moles of A from the balanced equation, moles of B. Okay. I don't know if you've noticed, I'm trying to match these diagonally. So mass on the left, mass on the bottom right. Moles on the left, moles on the bottom right. Okay. Then from here, finally, I have 1 mole of B and then mass also in grams. It has to be in grams of B. We're going to be writing this out a lot throughout the rest of this chapter, throughout the rest of this class, all the way to almost the last chapter. We're going to be doing mass to mass stoichiometry. You hear about mass to mass, moles to moles, all that stuff. Okay. And I don't know if you've heard stories about stoichiometry. People are like, ooh, stoichiometry. I'm like, well, to be honest with you, when I first learned about it, I was like, what in the world is this? And I had taken a math class. I was like, this is horrible. This is nothing like math. Chemists take math and ruin it, right? I had that attitude. Once I got what we're doing, I was like, oh, okay. We're doing this all the time. This is a routine. I went from hating it, not understanding it, asking why, to going, oh, do we do this all the time? And this is the purpose? Okay, I got it. Okay. So we will actually work out if you're going from mass to mass, this is the greatest conversion. And because it's the greater conversion, you have to go through three conversion factors to land in your correct unit. If you're only going from mass of A to moles of B, it takes you two conversion factors to get there. If you're going from mass of A to moles of A, it takes you one conversion factor. It depends on where you're trying to head to, right? For mass of A, moles of A, one conversion factor. Mass of A, moles of B, two conversion factors. Mass of A, mass of B, mass to mass, three conversion factors. Okay, so the further out you're trying to go, the more conversion factors. So let's see here. Same equation. Let me be a little lazy here. Or should I say more efficient? I am going to take this here. Okay. And I am going to, write the question. So this is my balance equation. Oh, by the way, stoichiometry begins with the balance equation, right? So I usually like to write my balance equation first and then write the given information. So here's my balance equation I'm going to be using, same one. It says determine the mass in grams, because the masses are usually in grams, of CO2. So I'm going to stop right here and then right here. What is wanted is this number here. When I get it, it's going to be in grams. Okay, I'm solving for that. Okay. Produced when 3.6 times 10 power 15 grams of this reactant. Wait, what? 3.6. Given 3.6 times 10 power 15 grams of octane. So we're given a huge amount of octane is burned in excess oxygen. So we have our two participants that we're focusing on right now in our stoichiometry, right? We have our given amount and we have our wanted amount. They're both in grams. I know that since I have this chemical here, I'm going to have to undergo three conversions, right? Three conversions. Periodic table, balanced equation, periodic table. So PT, BE, PT. Let me write it out. You start with the given number, which is going to be 3.6 times 10 power 15 grams of the formula C8H18. Then you draw your conversion bracket. Here's my conversion bracket. Okay. I know my first conversion here comes from the periodic table. Okay. In the periodic table, the format is always, since I started off with grams here, I have to have grams of C8H18 on the bottom, right? Because the units have to match diagonally for the conversion brackets to work according to dimension analysis, what we've been doing so far, right? So up here, I have to have 1 mole of C8H18. Okay, so let me go through and I'll tell you what I was doing when I was a student, okay? It's 1 mole here, regardless of what is listed on the balance equation. What is what is listed on the balance equation has little to nothing to do with the number you write here. This is saying that all the masses in the periodic table are masses that were measured with a 1 mole amount of the chemical. That's why this is called the molar mass. Okay? So, for 1 mole of that chemical, C8H18, what's the mass? You're going to find your periodic table and then you're going to write this out. So, I'm going to write this out down here. Molar mass, right? Which is pretty much periodic table mass. I won't always write this out. In my formula, I have 8 carbons plus 18 hydrogens. Okay, each carbon is what? 12. Each hydrogen is what? 1. So I have 8 times 12 plus 18 times 1. Oh, 114. 114. So we're saying 1 mole of octane weighs 114 grams. Okay, I'm done with my periodic table conversion. Now my next one is my balanced equation. In my balanced equation, I always get my mole to mole. Okay, so that's where you use the molar amounts, the coefficient amounts from the balanced equation. Remember, I'm trying to match the units diagonally, so I'm going to write here mole of C8H18 on the bottom, mole of CO2 on top, right? Because they have to match diagonally. Okay, the number before C8H18 in the balanced equation is 2. The number before CO2 in the balanced equation is 16. I'm done with the balanced equation. Back to my other periodic table conversion. So I'm going to cancel my units for right now. I'm not done yet. I'm just trying to see how far I have progressed. Now down here, since I have mole of CO2, I'm going to write mole of CO2 down here. Once again, back to that periodic table where I'm trying to get the molar mass, right? This time I'm doing it for CO2. So it says I have 1 carbon plus 2 oxygens. 1 carbon is 12. 2 oxygen is what? 16 for each. So I'm going to put here 1 open parenthesis 12 plus 2 open parenthesis 16. What do I get? 44. Okay, so 1 mole of CO2 has 44 grams of CO2. Okay, mole of CO2 cancels out with mole of CO2. I end up with grams. So please notice in the periodic table conversion. So let me write this out in words. In the periodic table conversion, comma, number of moles is always 1. Okay? The number of moles is always 1. Now that we have this, let's go ahead and do our math. So you want to multiply all the top numbers, divide all the bottom numbers. So what I mean by this is 3.6 times 10 power 15. Okay, I am going to use parentheses here. Please do. Okay, times 16 times 44 divide by 114 divide by 2, and that will give me my answer, okay? I'm going to input it like that. So I'm going to write open parentheses, open 3.6 exponent 1.5 to the right, close, times 16 times 44 divided by 114 divided by 2. Okay, so I get the number 1.11 times 10 power 16 grams of CO2. Okay, 1.11 times 10 power 16 grams of CO2. Okay, probably going to be just 1.1 because remember they have two significant figures here. So let me rewrite this as 1.1. 1.1 times 10 power 16 grams of CO2. Okay, let's see what they get. Yeah, 1.1. In this next problem here, okay, let me copy the question out. So I want to say I used to hate word problems, right? I'm a lot more comfortable with them right now. I went from, let's see, a level of hate, if there's such a thing. Let's say liking. I went from liking them a 2%. Now I'm like, as a teacher, let's say a strong 90. Not bad, right? From like a really, really low like level to a much higher like level. It was more the intimidation factor, right? Knowing very well words weren't my strong suit. And then you have a question where the even though I talk a lot, I know, but the author is like wordy, and you're like, okay, but this is not like an enjoyable conversation. This is we're talking about you asking me as a problem I have to solve, right? But now I'm able to not really get into the head of the author, but try to think of things from their point of view. What are they trying to tell me? And what should I know? And so that helps me navigate through the question without being so boggled up with the number of words used. Okay. So here's the thing. The context of this conversation, everything we're doing right now, context is stoichiometry, right? Where we're doing mass to mass conversions, whatever. That's the context. So in that context, within the context, it says here, in photosynthesis, plants convert carbon dioxide and water into glucose according to the reaction. Photosynthesis. Sorry, stoichiometry always begins with a balanced equation. Do I have my balanced equation? Yep, right there. So I'm going to copy it and paste it. From the information I got, my first information I wanted, my balanced equation. Suppose you determine that a particular plant consumes 37.8 grams of CO2. Yeah, there's a lot of words communicated here, but they're trying to tell me you were given 37.8 grams of CO2, right? The plant is using up that's the biology language, but the chemistry language is given 37.8 grams of CO2. Because in the stoichiometry equation, all you really want, bottom line, the given and what's the wanted? Given units, wanted units. Everything else is just extra words, right? In 1 week. Assuming that there is more than enough water present, okay, there's more than enough water present to react with all the CO2. What mass of glucose? Finally, there's a what? Wanted. Mass. Units. Grams. Okay? So then once again, I needed three things from here. The balance equation, the given chemical identified, the wanted chemical identified, the given number and units provided that happened, the wanted, well, we're looking for the value, right? But the units. I got what I wanted. Everything else is just extra information. Okay. Okay. Now start. I'm going from grams to grams. So 3 conversions, right? My gram of given. And then when I do my mole to mole, I'll go from here to here. Okay. So what am I doing again? Oh yeah, 37.8 grams of CO2. This is my first chemical. I'm going to draw my conversion brackets. I know I'm going to go through 3 sets, right? My first conversion is periodic table. Second one is balanced equation. Third one is periodic table. I know that. Okay. So grams of CO2 are right here, grams of CO2. And then this is going to be 1 mole of CO2. Okay. What's the gram of CO2? Carbon is 12. 2 oxygens are 16, like that. So I end up with 44 grams, 44. Okay. From the balance equation, I'm getting my mole to mole ratio, mole to mole. Okay. Wait, grams of CO2 cancel out. Down here, I'm going to have my mole of CO2, right? Which is my given quantity, or not quantity, but my given formula. Then my wanted formula is going to be mole of C6H12O6. Okay, the coefficient here becomes the moles here. The coefficient here becomes the moles here. Okay, moving on. Finally, down here, I have to write mole of C6H12O6. Remember, periodic table moles are always 1 mole, regardless of the coefficient written in the balance equation. This is always 1 mole. Then the amount here is 6 carbons. Carbons are 12, plus 12 oxygen, 12 hydrogen. Hydrogens are 1, plus 6 oxygens. Oxygens are 16. Add all this up, I get 180. So 180 grams of C6H12O6, right? Okay, let me erase all this, working this out. Let me cancel out the units I don't need. So my answer will be in the unit of grams of C6H12O6. Is that what we're looking for? Yeah, that's what we're looking for right here. Let me work it out. What do I get? I write this as 37.8 times 1 times 1 times 180 divided by 44 divided by 6. What do I get? My calculator. 37.8 times 1 times 1 times 180 divided by 44 divided by 6. If you're wondering why I divide by the denominators twice, because my calculator, when I do it that way, my calculator always understands what I mean. It understands these two numbers on the right to be on the bottom. If I do divide by, multiply by, it brings the 6 back on top and gives me the wrong answer. Okay. I have seen one girl in my class. She had a really expensive calculator, like hundreds of US dollars. Yeah, cost of calculator. I'm like, wow, keep this very carefully. I'm looking at it. Not that I was going to take it or anything, but I was like, she was able to write divide by multiply here, and it worked out right. And I was like, wow, your calculator is operating at a whole different level than mine. That's what a $10 calculator versus one that's $300, $400 does, right? She could write things in some kind of lazy way and it still worked out. I was like, wow. So realize that you have to know how your calculator interprets your numbers, right? I have adapted to my cheap calculator and I refuse to spend more money on a calculator than I have to, right? I want it barely functional, working, and blue color. So because of that, I have to adapt the way I put the numbers in. If you have a more high functioning calculator that you paid lots of money for, $200, $300, $500, you may not have to do all this. Okay, kudos to you. But you want to adapt to your calculator, if that makes sense. Because it's supposed to be a tool to help you, but if you don't adapt to it, you will get your answers given to you in the incorrect format. Okay, 25.8 grams of glucose. Let's see what we have here. They show you the conversion factors. Okay, 25.8. Yeah. Oh, another problem here. Here we have sulfuric acid. Okay. So what is unique about this problem here is the fact that our starting point is not grams, it's kilograms, okay? So if you've noticed in the mass to mass conversion, our starting point has always been, scoot over, hold on, let me get this. Yeah, so here's our question. I moved it out of context, well, out of the slide, and then here's our equation. So let me copy that, paste that. No, the whole thing, paste it. Okay, hold on. Copy, paste. Okay. Okay, there. I have my equation. Sulfuric acid is a component of acid rain that forms when sulfur dioxide, a pollutant, reacts with oxygen in the water according to the simplified reaction. So sulfur dioxide is produced by industry as a side product of chemical reaction. What happens to the sulfur dioxide? It goes to the atmosphere, meets with oxygen, rendezvous with the oxygen in the atmosphere and moisture, water, and then produces sulfuric acid. I'm like, ouch, sulfuric acid burns. And then it rains. It rains. It doesn't rain water rain. It rains sulfuric acid rain. Imagine being out there when this is coming down. I mean, the concentration is not so high enough for us to really notice it. But yeah, I'm like, I want to protect my hair from this acid rain. I don't want my hair to be that acidic. The generation of electricity used by a medium-sized home produces about 25 kilograms of sulfur dioxide per year. Yikes. Now I blame it on industry, right? This is telling you, as we're generating in our electricity in our homes, we are part of the problem. We're generating sulfur dioxide per year. How much is it? We're generating 25 kilograms. So underneath this whole message about how we are ruining the environment, that's the low-key message here, is the given information. Given SO2 per year. How much of it is given? 25 kilograms. But then while you're reading that, just so you know, you're contributing to the sulfur dioxide concentration in the atmosphere. Assuming that there is more than enough oxygen in the atmosphere and water, what is the mass of sulfuric acid in kilograms that can form? So what is wanted is the amount in kilograms. Ooh. That can form from this much SO2. When sulfur dioxide, 25 kilograms of it is consumed in the chemical reaction, how much sulfuric acid are we making? Okay, well, here's what's up, right? Our conversions since we started with the masses is masses in grams, but now we have kilograms. So I would say, okay, take a step back, convert write the given in two forms. The actual given, 25 kilograms, 25, can't forget that. And then you can just convert it to grams, okay? So I'm just going to show you on this side how I do it. 1 kilogram is a conversion factor 1,000 grams. So we end up with 25000 grams, okay? So the given is this form, 25000 grams, okay? I'm just writing the same number, well, not the same number, the number twice with different units, therefore different values, right? And for my conversion, the second number is more user friendly. So I kind of converted, I converted the number to a more user friendly form, which is grams, because my mass to mass conversion is not written for kilograms. You have to do one more conversion. Okay, so starting with my number in the correct unit, 25000 grams of SO2. Now I can start my dimensional analysis brackets. Okay, gram of SO2, again, periodic table, again, 1 mole of SO2. What is SO2 again? Sulfur. What is sulfur? Is it 16? Oh, mass of 32. Sulfur, 2 oxygen, 32 plus 2, 16, 64. Okay? And then this is balance equation. And then periodic table. Let's see. Balance equation is this chemical versus that chemical. So 2 moles SO2. Remember that the units have to match diagonally so they can cancel out diagonally, right? Then on the top I have 2 moles H2SO4. Okay. And then periodic table, I have 1 mole of H2SO4 and then grams of H2SO4. Okay? Okay. What's H2SO4? H plus, 2 H's plus 1 S plus 4 oxygens. 2 times 1 plus 32 plus 4 times 16. Okay, I need a calculator for that one. 2 times 1 plus 32 plus 4 parentheses 16, 98. 98 grams of sulfuric acid. Okay. Now let's see. This right here. Yeah. Okay. If I work this out and I stop right here, I'll get my answer in grams. But they want me to do one more step in kilograms. So what I'm going to do is add one more conversion, right? Up to here. So I'm going to add a curly divider. This is my curly divider right here. Up to here, this is the end of my traditional, now I'm calling it traditional mass to mass conversion. But I'm going to add this 1 kilogram, 1,000 grams. Okay, H2SO4, H2SO4. That will allow me to go from the gram unit into the kilogram unit they so desire. Okay, now I'll do my conversions. Start with the top, 25000 times 2 times 98 times, I guess 1, divided by 64, divided by 2, divided by 1000. Okay. According to them, I get a 38.28 kilogram. 38.28. 38.28. Okay. Let's see what they get. They probably have more space, so they combine it all together. Okay, what is this? I don't know what that is. What is this again? I don't know. Anyway, yeah. So you see how the traditional mass to mass conversion is right here, right? With the PT right here, with the BE right here, and the PT right here. But they have to bring in one more conversion to convert the kilogram into gram. And then here, the gram into kilogram. Okay, so they bring an additional step, and that works out. Okay, so 25 kilograms converted to grams, and then the conversion goes down here, and then ta-da, 38.28 is our answer. Okay. Finally, limiting reactant. I was saying to myself, when will we get to limiting reactant? Okay. In the limiting reactant concept, the idea is this. Okay. Let me detour for a little bit. But before I do that, let me define this. Limiting reactant is the reactant that makes the least amount of product. There's so many definitions to this limiting reactant. This is the first one. A limiting reactant. So let me take a step back a little bit, okay? Because I feel like even though according to the author we have transitioned into this, I usually like a little bit more background information. So let's assume you're dealing with a reactant where we have two reactants. So we have reactant A and reactant B. Okay, this is a scenario. And you're trying to get two reactants to react with each other. So when you have just enough of each reactant, okay, with exact amounts of each reactants, comma, the reaction will yield, which is make products, will yield products with no extra reactant left over. Okay, this kind of reminds me of if you've ever bought one of them pre-packaged recipes. Okay, one time, well, I've had opportunities a few times where they have those pre-packaged recipes. So it's like, get a chance to cook this recipe at home, and here are the reactants, and they give you exact amounts of each ingredient, right? They tell you, well, take the meat available, and they measure that meat to a T. And the meat is seasoned. And then two tomatoes, and guess what you have? Exactly two tomatoes. And then five oranges. Okay, I'm just making it up because you're like, oranges. Okay, yeah, I'm just making this up. But everything you need for that, the only thing I feel like is sort of exact, but they give you leeway on is the seasoning, right? Because that one tends to be you get to choose how much of it. So I would say in those kind of situations where I've had prepackaged recipes and stuff, everything was exact except for the flavor, the seasoning, because they tell you use as much as you want. You know, I'm using the almost the whole packet, right? Because I'm like, if they gave it to me, more is better. Anyway, so imagine they gave you pre-packaged amount, exact amounts of everything you need. So once you mix all your ingredients to make your food or whatever, you don't have any left over. So when everything is done to make your product, you have no extra reactants. I kind of like cooking that way. It's kind of a lazy way, but you don't mess it up a lot. You don't have a lot of leftover, and then you don't have waste. So when you're throwing stuff in the trash, it's just the wrappers and stuff, not a lot of extra peels and stuff. The kitchen doesn't get too dirty. You get the idea, right? You don't have leftovers. So there is a name for the exact amounts of each reactant. This is called stoichiometric amounts. Stoichiometric amounts. So this is when you have exactly what is needed for that balanced equation. So in the world of cooking, you say, oh, pre-measured, pre-packaged, pre-whatever. In the world of chemistry, the same description for the exact amount of each reactant is stoichiometric amount. Okay. So they say, okay, imagine you have stoichiometric amount, meaning exact amount you need, there will be no leftovers. Okay. But what if real life hits? This is when you're trying to make your own recipe or you're trying to save money, so you bought a dozen eggs, but you only need two. So this is stoichiometric amount, scenario one. And then this is more like the reality. And the reality is when you have reactant A plus reactant B, but reactant B is the one that you have too much of. Okay, for whatever reason, maybe because if you got a package deal, you needed 2 grams, but if you got 10 grams, you got $5 off. You know what kind of deals? If you like to buy deals and stuff like that, I love to buy deals, and sometimes I buy things and I'm like, I don't need all of this, but I save $5. Now I have extra amounts I don't really need. So when you have too much of one reactant, by default, compared to reactant B, you end up with less than matching, right? Or should I say compatible, matching amount of A. So if you have too much of B, because you have too much of B compared to B, you don't have enough of A, right? They're not stoichiometrically balanced anymore. Now you have too much. The reactant that you have too much of is called the excess reactant. That makes sense. It's excess, too much, too much. And then the one that you don't have enough of just because you have too much of the other one, this is called limiting. What? Yeah, limiting reactant or reagent. So why is this limiting not, less than? Okay. The context is a chemical reaction and what is happening in the lab, right? Versus just gathering items. So the idea is a reaction between A and B will continue until the limiting reactant A runs out. Because remember, we judged that we didn't have enough A, so the reaction will continue. It will start, it will continue, and it will continue to occur until A, which we don't have enough of. We started off with an imbalanced amount of A and B, right? Until A runs out. When A runs out, the reaction is over. So we judge the limiting reactant as the one that runs out first in chemical reaction. Okay? It runs out. It's like, yeah, we didn't start off with enough amount, so it runs out. It runs out first. And when it runs out, not only does it run out, number one, it stops the reaction. Because in order for the reaction to take place, we need both A and B to be present. But now A has run out, so the reaction is over. But B is like, there's a lot of B. It's like, it doesn't matter though. A is gone, the reaction is over. So, limiting reactant runs out first. First definition, stops reaction. Second definition, determines amount of product. Third definition, to make the product you need both reactants present. Once the limiting reactant leaves, you can't make any additional product because the limiting reactant left. It limited the reaction, it stops the reaction. So I hope you see how we, in context, how we come up with those three strong definitions or characteristics of a limiting reactant. You start off with less than needed. It runs out first. By running out, it stops the reaction. Because it stops the reaction, it determines the amount of product made. Okay? Same chemical reactant. Okay. So when we go back, well, on the bottom here, it tells you limiting reactant is the reactant that makes least amount of product. And we'll look at that later on. Limiting reactant runs out first in the chemical reaction, causing the reaction to stop. Limiting reactant is also known as limiting reagent. The maximum number of product that can be made depends on the limiting reactant. So I just showed you in context what happens, right? In the chemical reaction, this is called the theoretical yield. Okay, so I'm working on definitions right now as I get to a certain point. Okay, what is theoretical yield? Okay, in chemistry or in science, theoretical is the term used to describe if all conditions are perfect. Okay, so it says here theoretical yield is the amount of product that can be made in a chemical reaction based on the amount of limiting reaction. Remember how I told you guys the limiting reaction determines how much product is made? So we're told here theoretical yield is the maximum. They didn't say maximum, but it's a maximum amount of product that can be made in the chemical reaction. And it is based on the amount of limiting reactant that was present. Because remember, once the limiting reactant runs out, the reaction is over. Whatever product you made, that's it. Okay, and then we're told it is the reagent that makes the least amount of product, determines how many product theoretical yield can be made. This here is talking about the limiting reagent. The limiting reagent is the reagent that makes the least amount of product. So I feel like the definition we're kind of going around in circles. It's just they're just redefining it. Theoretical yield is made by limiting reagents. So before we continue anything, limiting reagent makes product. Product is called theoretical yield. Okay, I'm trying to make this as linear as possible, where I'm trying to make it sound like something comes right after something, even though in reality, experiencing and learning this stuff is not linear. Okay, when you're learning something, it would be nice if everything was linear and everything just came out of the other, but it doesn't. Okay, here's the thing. Why not just call it product? Why this fancy name theoretical yield? Okay, and then at the theoretical yield, what is this actual yield? also called experimental yield, right? So theoretical yield, we know theoretical yield is the product made by limiting reagent, right? The theoretical yield is made by limiting reagent. Okay? I'm just paraphrasing the first statement. Okay? Second statement, the theoretical yield is also the maximum amount of product that can be made in the lab. Now I'm bringing up lab actions. Okay. What do I mean by this statement here, in the lab? Before we go to the lab, so this part here, theoretical yield, makes sense when we're going to the lab. Normally in chemistry, so normally in chem experiments, comma, the identity of the product to be made is known before experiment starts. It's not a secret. We're not doing research. When you're doing research, is different, okay? So in research, but the very definition of research is kind of remind me of the Star Trek introduction. I think this is the Star Trek introduction. Was like going to the places unknown and doing things that we don't know to find out things that we want to know, you know? Research, you're going to places that you don't know. So you don't know the outcome, right? You're like, okay, we're gonna go there, we're gonna kind of like an adventure. Research is a chemical adventure in the lab. When you're doing research experiments, it's different. What I'm talking about here is experiments that are not research. You're going into the lab and the outcome is known. You know before you get in there what product you're going to make before you even start the experiment. Okay? So when the product is known, we also know the amount. So the amount to be made is also known. The amount you're going to make that is known is called the theoretical yield. So essentially, this is the statement you're making. Before I go into the lab, I know I'm going to make a product. Whatever the product is, let's say you're doing an experiment between sodium hydroxide and HCl. I brought this back here, and you're making sodium chloride and H2O. So you're saying, before I go to the lab, I will be making table salt sodium chloride. I know what I'll be making. I know how much I'll be making. And then you go to the lab and you do the experiment. So let's say you're supposed to get 10 grams of sodium chloride. You do the experiment, but then you get 9.7 grams of sodium chloride. When you're reporting this, how do you report this? So you say the amount that you knew was supposed to be made, the theoretical yield, was supposed to be 10 grams. If everything was perfect, your technique was on point, no problem, 10 grams. But you did the work and then you didn't really fail, you just didn't get the number you got. You got 9.7 grams. What do we call this? We call the number you actually get in the lab the actual yield or experimental yield. So when you're in school, the teacher determines the quality of your work by your grade, right? How you're doing in your class, the level of understanding you have, the way you communicate. When you get to a job where you're doing a lab experiment and say you're a lab tech, how does your boss know you're a good employee, right? So once upon a time, years ago, I used to be a lab tech. My boss would determine how well I was doing the job by looking at my experimental yield, what I actually got, versus what I should have gotten. So it was an objective way of figuring out. Now we can do this in chemistry lab, but if you're a secretary or something else, how do they do that? I don't know. That's a different world. I don't work there. But he will compare my 9.7 grams of what I actually got versus the 10 grams, which is what I should have had, right? He's like, okay, not bad. She's not too far off, right? She's a little off, point 3 grams off, but not too far off. We shall not fire her. Well, we'll kind of give her a little bit of a bonus, right? Because she's close to the desired number. So the actual yield is the actual amount of product made in the chemical reaction versus the one that you wanted. So you can determine the efficiency of making your product as in the efficiency of your technique by figuring out a percent. Take the actual amount you made versus the theoretical amount you should have made. So theoretical to me is, imagine everything is perfect. Your chemicals are perfect. Your technique is perfect. That gives you 10 grams, right? You go in there and then you're kind of sloppy and you only get 9.7. So I can say here, take the 9.7 that you got versus the 10 that you wanted to get times 100, and we get 97% efficiency or yield. Okay? So this helps us actually figure out percent yield, right? How much we got versus how much we wanted to get. In industry, you want to make sure you maximize your yield, the maximum being 100%, because the more product you make, the more profit for the company, right? You want to get good quality product. You want to be able to get the percent they want you to get. If they want you to get 10 grams and you got 5 grams, there is a gap of 5 grams here that's being wasted. You're wasting profit. And so you want to improve your skill, right? Because the chemical you make equal money. So when we meet next, we will start here and do the math for this part. And then finish up the chapter. Okay? Any questions about this? Yeah, I'm trying to see what's happening next. Because I essentially went through the type of reactions. So the rest of this chapter is really just stoichiometry, until the types of reactions here. But yeah, I won't have to do much towards the end of this. But yeah, essentially, this is pretty much it. I will finish this chapter on Wednesday and then start the next part. Any questions? Okay, this is all I have for today. If you have any questions, just go ahead and if you have any questions, just go ahead and email me. Okay, thank you. Have a nice day.